In this video, we are going to go through the easy questions on the limitation of physical measurements. As usual, I suggest you have a go at the questions first by yourself and then come back and use the video to help you mark your answers. Okay, question 1, we've got to give 3 definitions. So the first one is a random error. A random error is when our results vary in an unpredictable way. So this is usually made by the person doing the experiment measuring incorrectly, and we can reduce it by taking more measurements, repeating our measurements, and then creating a mean. The next one is a systematic error. So this one is different than a random error, and it makes all of our measurements differ by the exact same amount. So results differ. A common example of this would be a zero error on some equipment that you are using to measure. Repeating your experiment would not remove the systematic error. You would need to work out what your systematic error was, and you could take that away from every single result you've got, or you could repeat your experiment after you've checked your equipment. And the final definition is an anomalous result, and that is when you have a value of your result that doesn't match the pattern. Most easy to spot when you've created a graph and there is one result that does not fit your line of best fit. On to 1b. Figure 1 shows part of a thermometer. Determine the correct reading on the thermometer with its absolute uncertainty. So if we have a look, it's going up to 28. So we can tell that by the fact there's 1, 2, 3, 4, 5 separate lines between 20 and 30, and that means each one, I'll write it as our resolution actually. Our resolution of our thermometer is 2 degrees C. So each one of those is 2 degrees C. So we've got 28 degrees C would be our reading. Then we've got to state its absolute uncertainty. So if you were to go on to Save My Exams, you will see that they claim the absolute uncertainty is plus or minus 1 degree C. However, that is for the AQA exam board. We are sitting the WJEC exam board. And in our notes, it states that to work out the absolute uncertainty of something like this, when we're just taking one measurement, we do plus or minus the resolution, which would be 2. We tend to write 28 plus or minus 2 degrees C and put our degrees C at the end. So that is our answer. If you see in the answers it says plus or minus 1 degree C, that is because that is for the AQA exam board, not the WJC. This is the correct answer for us. Question 1c. A student measures the time taken for the water at 0 degrees C to boil to 100 degrees C. Figure 2 shows the graph of the temperature against time. Circle the anomalous result. So that is this one here, because it is quite far from our line of best fit. 1d. State and explain whether the graph shows systematic or random errors and suggest a way to reduce this type of error. So it's not a systematic error because it goes through 0 here. If it was a systematic error, it would either come above or below, depending on what kind of error we had. So that means that there are random errors. And we can see that by looking at our graph. There's some up here, there's some down here. They are all scattered around the line of best fit, but they're inconsistent. They don't go up at one point and down at another. They're inconsistent across our line of best fit. So I'll write that down. Our points are scattered inconsistently around the line of best fit. And it also says suggest one way to reduce this. So we'll say repeat our measurements and take a mean. that would reduce the likelihood of random errors. Question 2a, state which two measurements a micrometer screw gauge could be used to measure. So you might have used a micrometer screw gauge in class, or we might not have got to that yet. It is made for taking very, very small measurements. So this one would be a good one. The length of a pencil, that's too big. That would be better to use something like a ruler that we use in class. Thickness of a sheet of paper, that would be a good one. And the thickness of a water pipe, that would also be a little bit large for that one. So it is the first one and the third one. Question 2b. A student records 5 repeat readings using a micrometer screw gauge in millimetres shown in Table 1. Calculate the average and give it to an appropriate number of significant figures. So hopefully you remembered how you calculate an average. We are going to add up all of these. If you add up all of those, you should get 6.13. We've got 5 bits of data there, so the next thing I'm going to do is divide that by 5. And if I write down exactly what I got on my calculator, it's 1.226. So that is our mean, but it does remind us to do it to an appropriate number of significant figures. So if we have a look, all of these ones up here are to 3 sig figs, okay? So we're going to round our answer to 3 significant figures, 1, 2, 3. So we're going to round here. This is a 6, it's above 5, so we're going to round up. So our answer is 1.23. Question 2c, give 2 reasons why taking repeat readings provides more accurate data. So it reduces the effect of random errors. And we can use it to identify anomalies. Question 2d. Another student repeats the same experiment using the screw gauge and obtains an average value of 1.53 plus or minus 0.03 millimeter. Calculate the percentage uncertainty, and again, put it to the right amount of significant figures. So when we're changing an absolute uncertainty into a percentage uncertainty, we take our absolute uncertainty, 0.03, and we divide it by our number, 1.53, and it's a percentage, so we have to remember to times it by 100 at the end. So what you will get is plus or minus 1.96078. That's exactly what came off my calculator. It goes on a little bit more, but we're going to round it to 3 significant figures because that's what we've got in the question. 1.53, that's 1, 2, 3 significant figures. So what we're going to do is we're going to write 1.53 plus or minus 1.96%. So I'd cut it off here, 1, 2, 3, and I don't need to round it up because the next number is a 0. So this is how we write our percentage uncertainty. We write the number in full, then our plus or minus, then our percentage with our percentage sign at the end. And we probably should actually sneak a millimeter sign in there before our plus or minus. Next question, 3a. Figure 3 shows part of an ammeter. Determine the correct reading and give its absolute uncertainty. So if we have a look at this, each one of these represents 0.2. That is our resolution. 0.2 milliamps if we have a look at our unit. And this is 1, 2, 3, I'd say 3.5 little sections. So it's going to be 1.2, 1.4, 1.6, I would say 1.7 milliamps. So that'll probably get you your first mark. And then we need to work out its absolute uncertainty. So again, this question differs between exam boards. We are doing the WJC. It's going to be plus or minus whatever the resolution is of the device that we're looking at. So here it's going to be 0.2 milliamps. So what we tend to do when we write it like this is we get rid of the units here and we just put our units at the end, 1.7 plus or minus 0.2 milliamps. On to question 3b. We are setting up an experiment to check whether something obeys Ohm's law. We're going to use a digital voltmeter with a precision of 0.1 volts and an analog ammeter 0.01 amps. you're going to vary them both and then calculate the resistance. So first of all, what is our independent and dependent variable? So our independent, our IV, that's what we change. So that is our voltage or potential difference through the voltmeter. That is what we are changing. And what we are measuring, that's our dependent variable, is our current. And we are using the ammeter to measure that. Question 3C, correct the errors in the way the ammeter readings have been recorded. So if you have a look at this table, everything here is to two significant figures. Everything here is to one significant figure technically, and in this column, our ammeter one, it is a little bit inconsistent. So what we're going to do is we're going to do each one to three significant figures. I can see that this is precise enough ammeter, and it does tell us up here 0.01 amps. It has a strong high resolution. We can measure it correctly to those two significant figures. So we're going to add a 0 on the end here, a 0 on the end here, and a 0 on the end there. That doesn't make any difference to the value of that number. However, it does show that our device is precise enough to measure to two significant figures, and we should always make sure our tables are consistent with the amount of significant figures that we are recording it to. So it's to two significant figures for that one. Okay, question 3D. We're still talking about the same experiment, and we're wondering how can we reduce the effect of systematic and random errors. So if we start with our systematic error, so usually these are caused by zero errors. So what we're going to do is we're going to ensure the ammeter is set to 0 before we do any measurements. And then we've got to think about our random error. So we're going to take repeat measurements. To calculate a mean. And to spot anomalies. Question 4a, state clearly the difference between precise and accurate measurements. So a precise measurement means there's going to be very little variation around the mean value. So all of your results will be very close together. That would mean they're very precise. However, what you really want is also some accurate data. So that means your results are close to the true value. So you can check that by checking with other people who have done the experiment or checking the results online. Question 4b. Define the resolution of a measuring instrument. So you've got a nice definition for this written in your class booklet. It is the smallest change in the quantity being measured that can be observed. Basically, it's just how precise is your measuring equipment. So if your measuring instrument can measure to every single millimetre, its resolution is plus or minus 1 millimetre. That's all that question is asking. And 4C, a student uses a stopwatch to measure the time taken for one complete swing of a pendulum. They determine the time taken for 10 complete swings to be 8.4 plus or minus 0.1 seconds. Calculate the mean time with its absolute uncertainty and a percentage uncertainty, and don't forget to give it an appropriate number of significant figures. So first thing that we're going to do, if 10 swings takes 8.4 seconds, we're going to divide it by 10. and that means it's 0.84 seconds per swing. Then we've got to look at our absolute uncertainty. So we haven't looked at this before, but just so you know, when we've got an absolute uncertainty, so absolute here, and that one's for 10 swings. If we're going to do it to just one swing, we've divided our number by 10. You are also going to divide that by 10 as well, 0.01. So that means that for one swing, it's going to be 0.84 plus or minus 0.01 seconds. So you can see that our uncertainty has decreased. So that means our results are basically better because we've done it over 10 swings rather than one. Our results are more precise. We also need to work out its percentage uncertainty. So to calculate that, we do 0.01, our absolute uncertainty that we just calculated. We divide it by 0.84, and because it's our percentage uncertainty, we then times it by 100. If you type that into your calculator, you'll get 1.190476, and it continues. We now need to work out how many significant figures would be appropriate. So if we have a look at the data we were given in the question, 8.4, that is to 2 significant figures. So I'm going to give my answer to 2 significant figures. So I'm going to round this. So that's 1 significant figure, that's 2 significant figures. I'm going to round it here. The 9 is above 5, so we're going to round up. So we're going to end up with 0.84 seconds plus or minus 1.2%. Question 4D. There are some occasions where the resolution is not the limiting factor of the uncertainty in a measurement. State one other limiting factor that is going to affect the uncertainty in the time measured from a stopwatch. So this is going to be our human error, things that we get wrong, but we're going to try and be precise in our answer, and we're going to say it's the reaction time of the experimenter. So the person taking the measurements is likely to be a little bit slow as they press the button on their stopwatch. Question 5a. A vernier caliper has a systematic zero error of plus 0.10 millimeters. A student uses this to measure the length of a wire under various loads and records them in the table below. Determine the correct readings of length for each load. So we know that this is adding 0.10 millimeters to all of our answers. So all we need to do is take away 0.10 from all of our answers. So you're going to get 290, 344, 392, 451, and 4.89. Feel free to use your calculator if you're feeling lazy. One thing I am going to point out is this one up here, the 2.90. I wrote 2.90. I did not just write 2.9. That is so that everything is consistent in this column. Everything should be to 3 significant figures because that is how much we can measure accurately to. Okay, question 5b. A student wants to measure the extension. A proportion of the results table is shown in table 2. The vernier caliper scales have an uncertainty of 0.1 millimeter. Calculate the extension of the wire and its absolute uncertainty from the data shown below. So the extension of a wire is going to be how much it changes. So we'll do 3.54, take away 3.00. So that's going to be 0.54 millimeters. So that is our extension. And then we need to work out its uncertainty. So because now we're looking at 2 measurements rather than 1, what happens is that our uncertainty increases. So it was plus or minus 0.01, but it was also for this piece of data plus or minus 0.01. So what happens whether we're adding or subtracting 2 different numbers, when we look at their absolute uncertainty, we add them. So this time we're just going to add 0.01 plus 0.01. So it's 0.02. So that is our absolute uncertainty. So the way we write that, 0.54 plus or minus 0.02 millimeters. On to our final page, question 5c. Another student decides to use a ruler to measure the length of wire for each load and records it in table 3. The ruler has an uncertainty of plus or minus 1 millimeter. Calculate the percentage uncertainty when we look at this load. So we take our absolute uncertainty 1, we divide it by 2.5, and a percentage, so we don't forget to times it by 100 at the end, and you are going to get 20%. So we have to have a look. Do we need to check our significant figures? It's 5.00 plus or minus, so we match our significant figures in our percentage uncertainty to our original number. So this is given to 3 significant figures, so we can say 20.0%. And we'll sneak in our millimetres there because I forgot. So it's 5 millimetres plus or minus 20%. And final question, 5D. The student using a vernier caliper to measure the length obtained 4.61 millimetres plus or minus 0.01 when he puts this load on there. They state the percentage uncertainty is 0.22%. State and explain whether or not the student is correct. So we're going to do the same things we did for our last question. We pop the absolute uncertainty over our value, and then we times it by 100. You are going to get 0.217%, 23 sig figs. So again, our question is to 3 significant figures. So our answer should be to 3 significant figures. So that is not the same as 0.22%. They have rounded it to 2 significant figures, but we did not need to. So if you did round it up, you would get this answer. However, this was asking if it's exactly the same, and because this is to the wrong amount of significant figures, this one is wrong. They are not correct.